Session 5 for the Model 1 for the earthquake engineering. We're going to today see the numerical examples which are related to the Model 1. Here we'll see the varieties of the numerical examples related with the seismic velocities, then magnitude, intensities, and finding the epicentral distance. All together we will see it. So the first example is, let us see that the example is that at a recording station, a difference in time of arrival between P waves and S waves was observed to be 1.5 seconds. Then what is the approximate distance from the station at which the event occurred? Assume P waves velocity as 4 km per second and S velocity as 2 km per second. So here the whatever the two velocities are known to us, and the difference in the time is also known to us. Let us see that how we can calculate the distance. So here the whatever the first velocity, that is the P velocity, is 4 km per second, and the Vp we can call it as a 4,000 meter per second. So kilometer to meter it is converted, and similarly the S wave velocity is 2 km is there, so per second, so it is Vs is 2000 meter per second, and here the time whatever between the P and St is given as 1.5. So our the known equations for the distance calculation is S is equal to T divided by 1 by Vs minus 1 by Vp is there. You substitute T, Vs and Vp, so it gives us to 6000 meters, so that is 6 kilometers. So like that the distance can be calculated based on the knowing the time interval as well as the velocities of P and S waves. Now let us take the another example. So in this example it said that calculate the moment magnitude of an earthquake with the rupture area, dimensions of length 35 kilometer, weight 15 meter, and slip is 1 meter, and the whatever the assume the modulus of rigidity mu as 3.5 into 10 raised to 10 Newton per meter square. Now let us see that the given data whatever it is there. So here the length of the rupture area of the fault is 35 kilometer and width is 1.15 kilometers. So whatever the area is there of that fault is 35 by 15 meter, and here the slip whatever it is going to take place average it is a 1 meter. So this is the whatever the given data. So now as far as the seismic moment equation is there, so it is a mu times of a naught into d. So here mu is nothing but the modulus of rigidity is given, and the a naught is the area of the ruptured fault, so that is nothing but length into width of that ruptured part of area, and the d is nothing but the slip. You just substitute the corresponding values. Everything should be there in the same unit. So the whatever 35 and 15 kilometer is there, so you convert it. So 35 into 1000 and 15 into 1000, whereas mu is 3.5 into 10 raised to 10 and slip is 1 meter. So now the total seismic moment according to this equation is works to 1.84 into 10 raised to 9 Newton per meter. But we need to calculate the earthquake magnitude, and whatever the earthquake magnitude is there, MW is nothing but two-third of whatever the seismic moment M naught is there minus 9.1. You just substitute the M naught value as 1.84 into 10 raised to 19 values, and so now the whatever the earthquake magnitude is works to 6.8. so 6.8 is the magnitude based on knowing the whatever the mu, that is modulus of rigidity, and the area of the fault and the depth of the slip. So based on that, one can calculate the magnitude. Now, next problem is related with the during an earthquake, the maximum amplitude recorded at a site by Wood Anderson seismograph is 20 centimeter. The maximum ground velocity is recorded was 25 centimeter per second. This site is to be found to be 75 kilometer from the epicenter. So we have to determine the magnitude as well as intensity of the earthquake. So let us see the given data. So here the whatever the area, so whatever the seismograph A is there, so it's a 20 centimeter is there, you convert it into meter, that is a 0.2 meter, and also you can convert this meter to micron, that is to be A is to be put in terms of micron, that is 0.2 into 10 raised to 6 micron, and whatever the site is there, which is the delta, so that distance is 75 kilometer, you just put as it is, and whatever the Vg is there, so that particular velocity of the ground is 25 centimeter per second. So now you just substitute the m is equal to a log of a is there, log of a is there, that is a m delta. So log of a is given, a is given, so you just substitute the corresponding values of m. So m is equal to log of a. So here a is 0.2 into 10 raised to 6, you substitute it, and or you can see it in the directly, we can have the equations. M is equal to m delta minus 1.73 log raised to base 10 into 100 divided by delta. So here the whatever the ma is there, it's nothing but log of 10 for the 0.2 into 10 raised to 6 is there, minus 1.73 log of 10 and 100 divided by delta. Here sir, delta is given as 75 kilometer, you substitute it, so that directly this empirical formulas gives you the m value as 5.1. but we need to find out the intensity. So intensity, for that there is again equation, modified Mercalli equations, MMI. So it is the log of 10 14 Vg divided by log of 2 is there. So here Vg is the given data of the velocity of the ground. So 25 is there, you just substitute as it is, so that in this equations we'll get as 8.45. So round it to a 8, that is the mmmax. So now with this we can have the magnitude as 5.1 as well as the intensity we got as 8. So like that the examples is to be solved based on this available empirical equations are concerned. Now let us move into the other type of the example. So here it is said that the epicentral intensity of an earthquake that occurred in 1870 is estimated to be 9 in MMI scale. Estimate the approximate magnitude of the earthquake. So here the given data is the intensity is given as 9, that is I naught, and whereas the formula for conversions for the equivalent earthquake magnitude as 2/3 of I naught plus 1, you substitute I naught here, so that 2/3 into 9 plus 1, so you will get 7. So 7 is the nothing but magnitude. So whatever the magnitude for this case of the MMI, 9 is 7. So this is the other examples which is related to conversion of intensity to magnitude. Now let's move to the next example. So in this example it is said that assume that the seismograph located at 1200 km from the epicenter of the earthquake, the records a maximum ground displacement as 15.6 mm for surface waves having the period of 20 seconds. Based on these assumptions, determine the surface wave magnitude, that is a magnitude we have to find out. So based on this example, the given datas are whatever the circumferences of the earth is there. So circumference of the earth, we have to take it as 4 into 10 raised to 7 meters. That is for a 360 degree. And here the distance to the seismograph is 1200 kilometer is given. So now whatever this 1200 kilometer is there, you convert it into 1.2 into 10 to 6 meter, and whatever the delta is there, so that we have to find out for this calculation. So here it is for 1.2 distance, and circumference is 4 into 10 raised to 7. So based on that, for a 360 degrees, so the delta, whatever that deviation is there for this distance, is 10.8 degrees. So that one is to be first we have to evaluate. So whatever the deviation is there, so it's a 10.8 degrees there. Now according to the given data, here it is a displacement is given, that is the a dash is 15.67. so we make it the into 10 raised to whatever the 3 is there, so that we can first convert it in terms of micro meters. So that's why it is a 15600. So that is after converting. So now the whatever the available equations for the surface magnitude, ms is equal to log of a dash plus 1.66 log of a plus 2 is there, and here a dash is given as the 15600, substitute there, and log of delta is given as 10.8, you substitute that one also and add to plus 2, so that we will going to get the surface wave magnitude as 7.9. so like that the with respect to the available epicentral distance as well as displacement and the whatever the time period, so that we can have the relations for the surface wave magnitude. So this is the examples for that. Now let us take the other type of example. So here it is assumed that during the major earthquake on the depth of fault of rupture is estimated to be 15 kilometer. The length of surface faulting is determined to be 600 kilometer, and average slip along the fault is 2.5 meter. Based on these assumptions, determine the moment magnitude. So here use the shear modulus equal to 3 into 10 raised to 10 Newton per meter square. And whatever our available the equations, known equations for this example is that m naught is equal to mu into af into d. So here m naught is nothing but seismic moment is to be expressed in terms of Newton meter, and mu is equal to shear modulus of the material along the fault plane. So here it is taken as 3 into 10 raised to 10 Newton per meter square, and af is equal to area of the fault plane. So it is 15 kilometer by 600 meters. So that's why 15 into 600, so that is 9,000 kilometer square is there. So convert it in terms of meter square. So it is works to 9 into 10 raised to 9. So many meter square, and delta is nothing but the average displacement of the fault is there, 2.5 meters. So directly we can substitute as m naught is equal to mu into af into d. So substitute mu, af as well as the d in the corresponding units, so that directly you will get m naught is equal to 6.75 into 10 raised to 20 Newton meter. So that much of the moment so that much of the moment magnitude is there. So now, so here we have to convert in terms of scale of the moment magnitudes in the range of 1 to 10. So for that, whatever the m naught is there, so that one is to be put in this equation as the mw is equal to minus 6 plus 0.67 log of m naught is there. So you substitute m naught value, which is in terms of Newton and meter, in these equations, and after substituting and adding these values here, that is moment magnitude is works to 8. So 8 is the moment magnitude is there. Now here as far as the calculation of the epicentral earthquake is there, so that is the location of earthquake epicenter. It is nothing but, already we have seen that it's a point on the earth's surface directly above the location of the rupture or a faulting, can be determined using the informations about two of these seismic waves. That is the first type of wave to consider when determining the epicenter of the earthquake is P waves, and actually these waves are referred to be primary or a compressional waves. The important characteristics of the P waves are they are fastest of the seismic waves and are first to arrive. Then the particles that waves passes through the move in the same direction as the wave itself, pushing and pulling direction. Now they travel through the solids, liquids and gases. So that is all about the P waves. And whereas the second type of wave is to be considered for determining the epicenter of the earthquake is S waves, and these waves are also referred as secondary or a shear waves. So S waves can also be characterized by the some unique properties. They travel slower than the P waves and they are second wave to arrive. So they travel perpendicular to the vibrations of the particles. S waves can pass through the solids but not through the liquid or gaseous. Now these two waves will get it from the seismogram. So already we have seen that seismogram is nothing but the graph output from a seismograph, which is used to determine the epicenter of the earthquake. When the consulting seismograms, the P waves always appear before the S waves as they travel faster, can travel through the three status of the matter as opposite to one. To determine the distance of the earthquake epicenter, so here we have three steps. The first step is that first we have to determine the arrival time of P and S waves, and second one, calculate the difference between arrival time of P waves and S waves, and third one is refer to the earthquake time travel graph. So it is a readily available graph, that is standard graph is available. So here in this case we have to determine the location on the graph where the two lines have difference in the y values equal to the time difference that have been calculated between the P waves and S waves times, and where x is the location of the distance from the epicentral distance. Okay, so let us see that this is a figure which is showing the earthquake the time travel gap. So here x ordinates will indicate epicentral distance is in terms of 10 raised to 3 kilometer, whereas the time travel is in terms of minutes. The first whatever the line is there, it's a P, and second line is a S waves, and here the other figure it is a P and S, how the waves are going to be measured from the seismograph. So here the first is the P waves and then followed by the S waves. So now let us take one example so that we will come to know that how to use this particular earthquake time travel graph. Suppose the P waves arise at t is equal to 1 second and S waves arise at t is equal to 6 seconds. So determine the distance of the earthquake epicenter. So here to follow this procedure to determine the distance of the earthquake epicenter. So the following step is to be followed. Now the first one is determine the arrival time of P and S waves. So here it is given, that is the arrival time of the P is 1 second and arrival time of the S is 6 seconds. Now what we have to do, we have to calculate the difference between arrival time of P and S waves, so that the time difference is 6 minus 1 is nothing but 5 seconds. Now refer to the earthquake time graph. So here in the earthquake time graph, so we have to determine the location on the graph where the two curves have the time difference equal to the time. So here it is according to this, after looking into the earthquake travel triangle, it is clear that the two curves have the difference of 5 units in the y direction, 5 units in the y direction. So we have to search here. So whatever the S and P is there, so we have to count that 5. So looking into the whatever the earthquake time travel gap, so now whatever the x is there, that is the epicentral x, so it is works to 3.4. So now whatever the epicentral earthquake distance is there, 3.4 into 10 raised to 3 is nothing but 3400. So whatever this example is there, so it is the 3400 kilometer. How this graphically, that is earthquake time travel graph, is helpful for the calculations of this epicentral distance. So now here let us see that how this we have seen that example, that how this epicentral distance is to be calculated. So now the first is that's the two seismic waves. P waves arrive first and S waves arrive the later, L and R waves. Okay, so now after the earthquake, the difference in arrival times of seismograph station can be used to calculate that distance, the seismograph, whatever the epicentral D is there. So that how it is to be calculated. Now we look into the time history of each one. So here the whatever the first the is there, P arrival. Okay, and then it is enter into the body waves as and then it is a S waves and the L waves. So like that the sequentially how it is there. So now here whatever the time interval is there, so here P minus S is nothing but the time interval, that is whatever the P waves and whatever the S wave is there. So now you can see that suppose if it is a 8 minute, 3 minute, if the P and S, so correspondingly you have to trace it at what will be there at 3 minutes. Suppose if it is a 3 minute is there, so X direction whatever it is there in the kilometer it is there. Suppose if it is a P and S waves, the difference is 8 minutes. So whatever the 8 minute difference is there, so that is a B. So A is a seismograph A 3 minute, B is seismograph A difference is 8 minutes, and C seismograph is L1 minutes. So like that 3 minimum seismographs are required to determine the exact location of the epicenter. So now here first step is that measure the time between P and S waves and use the time interval graph to get the distance. So here the distance, the first A, second one is B, C. So like that we can have the time. Okay, so time from this travel time curve. Okay, travel time curve. So now in continuation of that one, so if the average speed for all these waves are known, then use S and P, that is S minus P time formula, and the compute the distance between the recording stations. So here time is nothing but distance by velocity with the simple equations, and here distance we have to calculate. So now here the distance has the P waves as a Vp and S waves as a Vs, and if the Vs is less than Vp, okay, so both the originate at the same places and the hypocenter, okay, at the hypocenter, then they travel at the same distance. But S waves takes more time than the P waves. Then in that cases whatever the time taken for the S is calculated as Ts is equal to d by Vs, and similarly Tp is equal to d divided by Vp, that is velocities. Okay, d is the distance. Okay, so now we can have the travel distance, time difference is there. So now we can put it in these equations. So Ts minus Tp is equal to d by Vs minus d by Vp. Simplify it, take it d out, and we'll have the further simplification as d into Vp minus Vs by Vp into Vs. So now solve for the distance d. Now simplify d. So we will have Vp into Vs divided by Vp minus Vs into Ts minus Tp equation. So now you can see that how the three whatever the distances are calculated, the seismographs. So seismographs, that is D1, D2 and D3, that is whatever the three circles are there. So three circles, three stations are there. So here first what we have done, we have read the S and P times from the three seismographs. Then what we have done, we have computed the distance from each event recording stations, that is the D1, D2, D3 using S and P time formula. Then what we have done, we have draw the each circle of the radius di on the map. Okay, then overlapping point is the nothing but the location, whatever the overlapping point of all these three circles are there. So that is nothing but the source of the epicenter, or it is close to the hypocenter, so whatever it is there. So like that, the hypocenter is to be calculated. So these are the some few possible numerical examples.